So here we will draw the velocity time graph of a body. We take the velocity on the y-axis. So this is velocity here, which is always meter per second. And we take time on the x-axis, which is in second. In the first case, for time 0, the velocity is 5. So for time 0, velocity is 5. So this is 5 at this point. For the next, for time 1 second, velocity is again 5. For 1 second, velocity is again 5. So here. For time 2 seconds, the velocity is again 5. Again 5. This body for 3 seconds is also 5. So this body seems to be going at a constant speed, at a constant velocity. So if you notice here, this body is moving at a very constant velocity. For all the seconds, for all the time, the velocity is always 5 meter per second. Now if we join the graph, we will get like this, a straight line, which will continue to be, because it is moving at a constant velocity. So when the velocity time graph is parallel to the x-axis, we can say the body is moving with constant velocity. So let me describe this graph. This is the velocity versus time graph is parallel to the time axis. Which is the time axis? The x-axis. If it is parallel, we can say body is moving with constant velocity. Let us calculate the acceleration in this case. Now remember, we learned it last time. When is a body said to be accelerated? If there is a change in velocity, then the body is said to be accelerated. No change, no acceleration. So in this case, is there a change in velocity? Is the velocity changing? And we know here in this case, velocity constant means velocity does not change, which means acceleration equal to 0. No acceleration, because there is no change in velocity. So we have a graph of this kind which is parallel to the x-axis. We say the velocity is constant and there is no acceleration. Now we'll plot the velocity time graph of this body. At time 0, velocity is 0. So it would be here. Next is for time 5, velocity is 10. Time 5, velocity 10. So the body is here. Then next we have for time 10, the velocity is 20. Time 10, velocity 20. So it would be here. Then next for time 15, velocity 30. For time 15, velocity is 30. So your point will be here where 30 and 15 meet. Then at time 20, velocity 40. At time 20, velocity would be here 40, and that would be at this point. And last, at time 25, the velocity is at 50 here. And this would be a point. So this is the point we have plotted. So we'll now join the points. So this is our velocity time graph. Okay, it's a straight line. Now if you notice here, the velocity of the body keeps changing. If the velocity, and it keeps increasing. If the velocity of the body is increasing, it is changing, means the body is undergoing acceleration. Let us find the acceleration of this body. First, how do we find acceleration of the body? We do final velocity, which we take as v minus the initial velocity, which we take as u, over the time taken to change this velocity. So over here we'll calculate the acceleration between, say, this point A and say this point B. So at the point A, here it was the initial velocity. This was u. The velocity was how much at A? It was 10. So at A, the velocity is 10. And remember, meter per second. And then when the body went to B, the velocity increased. This is V. This is the final velocity. How much did the velocity become? It became 40. So the V is 40 meter per second. There was an increase in velocity from 10 to 40. Means there was an increase of 30. How long did this all take? At A, the time here was 5 seconds, and at B, the time was 20 seconds. So the time taken from A to B time taken would be 20 minus 5, and that would be 15 seconds. So we saw that the acceleration was v minus u over t. V was the final velocity at B, which was 40. U was the initial velocity at A, which was 10. And the time taken for this to change from 10 to 40 was 15 seconds. We calculated here. So this would be now 30 over 15. So it is 2 meter per second square. This was the acceleration. 2 meter per second square. That means for every second the velocity was increasing by 2 meter per second. So you've seen in this body the velocity increases a bit. How does it increase? The increases by equal amounts. Here the velocity increases by equal amounts in equal intervals of time. And such a motion is called uniform acceleration. So this is uniform acceleration, where the body increases its velocity by equal amounts every second. In this case, for every second it increases by 2 meters per second. Let us plot this graph again, time velocity graph. At 0 seconds, the body has a velocity of 8. So this is 0 seconds, the velocity of the body is here. Then they said at 1 second it has got 6. So this is 1 second, at 1 second it is 6. So it is at this point. Now at 2 seconds it is 4. 2 seconds is here, 4 is here, so it meets here. So 2 seconds it is 4. Then at 3 seconds it is 2. 3 seconds it is 2. So it is here. Then at 4 seconds it is 0. So at 4 seconds the velocity is 0. So it is here. This is the point. Okay, I will join the points. So here we join them up. Now if you notice here, the body is decreasing its velocity. It's coming down. So this is called retardation. Here the body is undergoing retardation. What do you mean by retardation? Velocity decreases. There is a fall in velocity. But here again, let us calculate the retardation. So say at this point here, between here and here we'll calculate the retardation. Say this is point now P and this is Q. P will be the initial, that is U, and Q is a final. So the initial for retardation PQ, let's find the initial velocity, that is U, and let us take the final velocity, and that is V. So initial velocity here is 6 and the final velocity we see in here is 0. And what is the time taken for this whole process? At P the time is 1, and at Q here the time will be 4. So this is the time taken. So time taken for this velocity from 6 to become 0 is 4 minus 1, that is 3 seconds. In 3 seconds the velocity drops from 6 to 4. So the acceleration, we know the formula of acceleration, V minus U over T. Final velocity minus initial velocity over T. So here acceleration, your final velocity is 0, your initial velocity was 6, and your time taken was 3. So it's minus 6 by 3 minus 2 meter per second square. Why did we get this negative? This negative indicates that there is a decrease, when there is a retardation taking place. Every time there is a decrease in velocity, your graph will come down like this and the acceleration will be negative. So in this case there is a retardation. Let's plot this graph. Time 0, velocity 0. So it's here. Then next we have time 1, velocity 4. Time 1, 4 would be somewhere maybe here. So we have here. Then next time 3, velocity 10. So it would be here. So we put this here. Then time 2 would be 6. Time 2 and the 6 would be somewhere here. So we'll put this here. Then time 4, velocity 16. So time 4, velocity 16 would be somewhere here. So this would be here. And then time 5, velocity 24. Time 5, velocity 24 would be somewhere here. So this point would be here. I will join the points up. And if we were to join the points up, you'll get something like this. Probably something like this. And if you notice here, we won't find the acceleration. Of course, the body is accelerated because the velocity is not same. The velocity changes. Here, velocity changes. If velocity changes, which means body is accelerated. And if you notice here, in this here, there is a change of 4 meter per second from first to the second. Then here there is a change of 2 meter per second. Then there is a change here of 4 meter per second. Here is a change of 6 meter per second. And here is a change of 8 meter per second. So there is no constant change. In 1 per second, the velocity changes by 4 meters, increases by 4, and in the next second it increases by 2, then again it increases by 4, then again it increases by 6, and then again it increases by 8. So the velocity does change, but not uniformly. Such motion where the velocity does not increase uniformly is called non-uniform acceleration. It is called non-uniform acceleration. So here we'll do non-uniform acceleration. Is when velocity, it could increase or it could also decrease by unequal amounts in equal intervals of time. That is called non-uniform acceleration. Non-uniform acceleration, velocity increases or decreases, but by unequal amounts in equal intervals of time, and that is non-uniform acceleration. So here again we'll write the velocity time graph. We'll just summarize. And if the velocity time graph is a straight line, this we say is uniform acceleration. Uniform acceleration, the body increases its velocity uniformly, equal amounts in equal intervals of time. But if the graph is this is non-uniform acceleration. And what you mean by non-uniform acceleration means body increases or decreases its velocity by unequal amounts in equal intervals of time. Now, together with acceleration, we also have retardation. If the graph is this straight down like this, means this is uniform retardation. Why uniform retardation? The velocity is decreasing, but uniformly. And if we have a graph something like this, also retardation, but this is non-uniform retardation. So we learned 4 kinds of graphs of acceleration. One is a uniform acceleration, which is a green one. The body increases velocity uniformly. The yellow one is non-uniform acceleration. Velocity increases, but in a non-uniform manner. Here, velocity also increases in a non-uniform manner. Here, velocity increases uniformly. And then we had retardation, where the velocity decreases in this case. Have you seen? The velocity keeps decreasing in a uniform manner. But in this case, the velocity also decreases, but in a non-uniform manner, unequal amounts in equal intervals of time.